When we talk about building data systems, we often ask what it means for an architecture to be good. It is a question with immediate engineering consequences. Without a precise vocabulary, we have no objective way to measure whether a system is built correctly, justify the investment required to build it, or explain the resulting compromises to stakeholders. Production systems are governed by three strict concerns: reliability, scalability, and maintainability. Most of the complexity we manage in modern infrastructure falls into one of these three categories. These properties are linked in a zero-sum relationship. Improving one usually penalizes another. Pulling the architecture toward greater scale applies immediate pressure to the struts connecting it to stability and maintenance. Data replication is a clear example. Adding redundant copies of your database nodes increases reliability, but those extra nodes instantly consume the maintainability budget by introducing complex consistency requirements and operational overhead. There is no universally superior database or replication strategy. There is only the mathematically optimal choice for a specific set of constraints and requirements. Consequently, the first duty of a system architect is not selecting technology, but quantifying the precise numerical requirements of the system's workload. Ignoring these fundamental trade-offs results in systems that either become impossible to operate under mounting technical debt or fail to meet the basic performance requirements of real-world traffic. The word scalable is meaningless without first identifying the specific quantitative stress being applied to the system. We define that stress using load parameters. These are the metrics that govern system pressure, such as request per second, the hit rate on a cache, or the exact read-to-write ratio. To see how load parameters dictate design, we can look at Twitter's early architecture. Their core problem was rendering a chronologically sorted home timeline for millions of concurrent users. Their first architectural attempt relied on fan-out on read. When a user posted a tweet, it was written once to a central database. When their followers opened the app, the system had to execute heavy SQL joins to retrieve all the posts from every followed account, sorting them by time. Conceptually, this is simple, but at scale, the computational cost of running massive joins every time any user refreshes their timeline overwhelms the database. Twitter shifted to fan-out on write because their load parameters showed users were reading 300 times more often than they were writing. Instead of assembling the timeline during the read, the system pre-computes it. One new post immediately spawns thousands of insertions directly into individual follower caches. By pushing data into a cache ahead of time, a user loading their timeline triggers a trivial, instant lookup. The architecture moves the computational burden away from the frequent read operations and places it on the less frequent write operations. Solving a scalability bottleneck is rarely about finding a faster database. It involves locating your heaviest processing tax and moving it to the lowest frequency behavior in your load profile. However, load parameters are rarely uniform. Data naturally clusters, creating areas of extreme data access skew. Twitter's social graph follows a severe power law distribution. A tiny fraction of accounts hold massive, disproportionate influence compared to the average user. This statistical skew reveals the specific scaling limit of the fan-out on write model. When a celebrity with tens of millions of followers publishes a single post, the design itself becomes the bottleneck. That single post generates an explosive spike of tens of millions of simultaneous cache insertions. The database attempts to write a massive volume of records in a single window, catastrophically overwhelming the write queues. Twitter's actual solution is a workload-specific hybrid. They use fan-out on write for average users, but for celebrities, they bypass the cache, using fan-out on read to merge those specific posts only when a follower requests them. Robust architectures avoid monolithic logic. They dynamically split their internal processing to handle the statistical realities of the common case differently than the extreme tail. When we shift from scaling data to measuring its speed, we have to distinguish between latency, the time a request spends waiting to be handled, and response time, which is the total time the system takes to execute the request and return the result. High-performance systems often hide their problems behind average response times. A healthy average can mask severe, system-breaking delays for a large percentage of your users. Response times rarely follow a neat, symmetrical bell curve. They form a heavily skewed, long-tailed distribution where a small number of requests take much longer than the rest. We measure this tail in percentiles, P95, P99, and P999. These numbers represent the experience of your slowest users. If your P99 is high, 1 out of every 100 requests is suffering from significant lag. Tail latency directly dictates revenue. Amazon found that every 100 milliseconds of added latency cost them 1% of sales. Google saw a 500 millisecond delay reduce search traffic by 20%. Variance also compounds. If a single page load relies on 100 different microservice calls, the probability of at least one of those calls hitting a P99 delay skyrockets. One slow database fetch can stall the entire user interface. If you are only monitoring average latency, you are statistically blind to the compounding degradation that drives users away. The primary cause of these tail latency spikes is queuing delay at the server level. We call this head-of-line blocking. A single complex, slow transaction at the front of the queue acts as a roadblock. Every fast request behind it is forced to wait, regardless of how simple it is to process. This creates coordinated omission, where benchmarking tools fail to measure true wait times. The server-side timer only starts when processing begins, but the client-side timer has been ticking up exponentially while the request sat idle in the queue. Because processing is often serialized, a server where 99% of requests are fast can still exhibit widespread failure if it is stalled by a single slow task. True performance monitoring requires measuring at the client edge. A fast server is irrelevant if the network queue leading into it is paralyzed. Reliability requires a strict distinction between a fault, a single component deviating from its specification, and a failure, which is the system as a whole failing to deliver service to the user. Components will break. Hard drives die, networks drop packets, and cosmic rays routinely flip bits in RAM. In any data center larger than a closet, some piece of hardware is always in a state of degradation. Attempting to engineer a fault-free system is impossible. The goal is fault tolerance, arranging the system so that component faults do not turn into user-visible failures. The standard mitigation for hardware faults is software-level redundancy. If a server dies, the system instantly shifts its workload elsewhere, making the physical failure invisible to the end user. A reliable system treats hardware death as a routine background operating condition rather than an emergency. Hardware faults are mostly independent, but software faults are correlated. A single bug triggered by a specific input strikes every redundant node running that software at the same moment. This triggers a cascading failure. One service degrades and slows down. The services relying on it time out and retry, creating an amplification cycle that overloads the degraded service and forces a wave of crashes across the network. Mechanical defenses like circuit breakers and load shedding protect the grid by aggressively refusing work, severing connections to the degraded zone before the entire system collapses under the retry load. To validate these mechanisms, we use chaos engineering. By deliberately injecting faults into production, like Netflix's Chaos Monkey terminating live servers, we can empirically prove the system survives the failures it claims to tolerate. If a system's fault tolerance is never actively tested, it is merely a hypothesis, not a guarantee. Building a data system is only the initial investment. Most of its total lifetime cost is generated during its years in production. Every architectural choice made today dictates the difficulty of operating and adapting that system long after the initial code is written. Maintainability is broken down into two traits: operability, the ease of keeping the system running, and evolvability, the ease of adapting it to changing requirements. Good abstraction is the primary weapon against complexity. Hiding messy implementation details behind clean interfaces allows engineers to change the underlying storage or logic without rewriting the entire application. Mature teams use service-level objectives as mathematical contracts to balance stability and speed. Violating an SLO forces a pause on new features until the system meets its reliability targets. An architecture designed strictly for 10 times today's load is often wrong. Requirements will mutate and new bottlenecks will emerge before that scale is ever reached. Designing data-intensive applications is not a search for the perfect technology. It is a constant negotiation with physical and mathematical constraints. Elite engineering is the disciplined, ongoing act of managing trade-offs, assuming continuous failure, and relentlessly prioritizing the reality of the workload over the illusion of the ideal system.